All right, what do we have for this first one? Solutions, what do you need?
Well, it's two substances, right?
Okay, so how about, what about the two substances, solute and the solvent?
They're homologous. That's fair.
So homogeneous mixture of a solute and a solvent? Okay. How are that solvent and that solute related to each other?
Solutes dissolve in the solvent.
Wait, say that again?
The solutes dissolve in the solvent, but at least there's more solvent than there is solute of the two substances that are there.
Okay, so what you said, other way around.
Is it the other way around? Is there more?
The solvent is dissolving the solute.
Oh, is the solute is dissolved in the solvent? Is-
Correct.
That's what it's saying.
Oh, that's not what that's not what I heard.
Yeah, sorry.
Okay. So, how about we just do this? A greater than sign? We need more whichever one's there in the greater quantity is the solvent. What happens to the solubility of a solid as the temp decreases? Up or down? It goes down. Why does the solubility decrease as temp decreases? Which molecules? How about this, my bad. How about the solvent? I just can't write today. They have less kinetic energy, so it takes more of them individually to keep the solute molecules or ions solubilized. How about solubility of a gas as the temp increases?
It's inverse.
Okay. So as my temp goes up, my solubility is going to also drop in this case. So for gases, it's the opposite. And what's the reason behind that? So the gas solute molecule's kinetic energy is increasing along with the solvent molecules, but in this case, the solute molecule can just leave as a gas, so it does. What do I need for this molarity equation and units and whatnot? Moles, solute, liters, solution. And it's a capital M. And so then your units are moles per liter. Alright, what's the concentration reported in units of moles per liter? 100 milliliters. Okay, so I've got potassium iodide. So I've got 140 grams of Ki, and I'm going to put that in 100 milliliters of solution. I'll make the 1,000 milliliters 1 liter, cancel those guys out. And then 1 mole of Ki, some number of grams of Ki. Where's my table? So, awesome. The periodic table disappeared. I have to go grab one next door. Let's see if that works out for me. Nope. How about that? Yep. Alright, so 166.28. 166.0028. So 140 divided by 166.0028. So I get 8.43 moles per liter. Looks like I have 1 sig fig here, so 8 moles per liter. Alright, so to answer this, will the potassium be dissolved at 20 and at 10 degrees Celsius? We're going to have to go back over to this. And then if I look at this, I've got 10 degrees Celsius here. I drive that up, and then I can get about 135 grams at 10 degrees Celsius. And at 20 degrees Celsius, I can get about 144 grams. So then my question over here will be, or my answer will be, yes. Awesome. Yes, at 20 degrees Celsius, and no at 10 degrees Celsius. I'm going to have like 5 or 6 leftover grams of potassium iodide as a solid sitting at the bottom of that 10 degrees Celsius. All right, so how do I make a 250 milliliter solution of sodium hydroxide? All right, so I'm going to need, what's the first thing that I need to do this? What would you do? Do we care about how many moles there are? Yeah, I care about how many grams there are. I'm not super concerned about the number of moles since I can't go get myself a mole value. So there's something else that's kind of important that maybe you want to check on beforehand, which would be what?
What the other substance was, what you're dissolving it in?
No, this is always going to be water. That you have a 250 milliliter vol flask. So I can't make 250 milliliters of it if I don't have a 250 milliliter vol flask. So I would say right off the bat here, get a 250 milliliter vol flask, because did we have them last week? We had the 25s? Yeah, in the other lab in Hood River, I didn't have any 25s, I only had 50s, and I don't have any 50s here, I've only got 25s, so you really gotta make sure you've got what it is that you're looking for, otherwise I can't do this. So I give myself a 250 milliliter vol flask, and then I need to figure out how many grams I need to put in there. So 0.35 moles of NaOH, and I'm going to have that a moles per liter. There's my concentration, but I'm only going to have 0.25 liters, and so for every 1 mole NaOH, it's 39.99715 grams NaOH. And then if I calculate that out with 2 sig figs, it ends up being 56 grams of NaOH. Is that right? No, I don't think that's right. It's 0.35 times 0.25 times 39.99715 equals, there we go. It's 3.4998 grams. So 2 sig figs, so 3.5 grams. So what I'm going to do now that I done my calculation, how about if I add that 3.5 grams to flask, half fill, mix, fill near line, and then fill 2 line with dropper, something like that. That way I don't go over. Are we good with that? Anybody got questions? No? What's the real difference between the molality and the molarity?
Dealing with either liquid or solid, or liters or mass.
A volume or mass?
Volume or mass. Doesn't necessarily need to be liters, but it's volume or mass. So this guy here is a volume calculation. And this one here is a mass calculation. And these are about solution. So with the molarity one, I'm calculating moles per volume of solution, and with the molality one, I'm calculating moles per mass of solution. Why would you do one over the other?
Molality is more accurate.
Okay, so this one more accurate, but it's going to end up costing you more money because you need a very expensive scale, and this one here is cheaper and pretty easy. The other thing with this one is it's not temperature dependent. Dent? E? Is there an A in that? Is there an A in that? Okay. Alright. That's all I got.